this is the mean value theorem. Well, you'll notice it's kind of similar. In fact, I didn't even have to erase the whole board. All I did was erase Rolle's theorem, and I erased the third hypothesis. These two hypotheses 1 and 2 are exactly the same as Rolle's theorem. My function is continuous on the closed interval AB, differentiable on the open interval AB. But now I no longer have the restriction that the function has to have the same value at the two endpoints of the interval. So my conclusion then is more complicated. My conclusion is not, oh, therefore I must have a horizontal tangent. I don't necessarily have a horizontal tangent. If it happened to be that f of a and f of b were the same, then I would, of course, have a horizontal tangent because this whole thing would be 0. But in most cases, I have something like this, right? So Rolle's theorem is a very specific case where these 2 points are the same. In most cases, I'm just going to say have something like this. Or maybe something that's very, easy looking, like it might have a lot of wiggles. But in any case, let's start with this picture. So here's my f of x. All right, so you can see from the way I drew this, there are no horizontal tangents in this picture, right? There's the maximum and the minimum, they're just going to be the endpoints. So, like, what am I doing here? Well, you can make a statement, though. And if you look at what this right-hand side is, this f of b minus f of a over b minus a, that should look vaguely familiar. I know it's been like a couple weeks, but that's kind of like the slope of the tangent line, right? So if I look at this slope of the tangent line, that's the slope of the secant line. Right, so if I look at the secant line between a f of a and b f of b, the slope of this line is that, right? Just the slope of the line. So what does this mean? It means that at some point in this interval, I've got some point on this curve where the slope of, that doesn't look quite right, but you get the idea. Let me try to make it a little bit better. Boop. All right, the slope of the tangent line is the same as the slope of the secant line. I can even think about it as a rate of change, but I'll talk about that in a minute, later. But so you have this geometric meaning, which I think is a little bit easier to remember than this with all these A's, B's, and C's, right? The geometric meaning is I've got the slope of this, I've got this secant line, but at least in one place in here, I can get the slope of the tangent line, which is the same thing. And in fact, this is really exactly what we did in Rolle's theorem, only we took this and put it down, right? So that it was a horizontal tangent line. Here it's not horizontal, it's something else, but you still have that same behavior. So this here is my point C. Okay. Now, like the situation with Rolle's theorem, there may be more than one point C. Let me draw something a little bit more complicated. That's probably not going to be the C, and C is probably not going to be in the same place, right? But let me make it like this. Okay? And now you can see I might have one C here and one C there. Something like that. That's fine. All this tells you is at least one point C. Okay? And then this is just rewriting this thing with putting this B minus A down here. Sometimes, when do you ever use this? Really, they use it if they're proving a theorem and they want to somehow get the derivative involved and know what the derivative is, then they'll use something like this, mean value theorem. So it happens quite often that people use this. But since we're not going to be proving, I'm not going to be having you guys prove theorems, you probably won't really be using this. I'll give you one example, one example kind of problem. The example problems are fairly simple. They basically ask you to find the point C in either this situation or in the Rolle's theorem situation. So they're very simple problems. Okay. The idea, though, to get in your mind is a good one. you do need these two hypotheses, otherwise it's not true. We can make examples where if you lose continuity or if you lose differentiability, you're not going to be able to find that point. Okay, now I just want to say something very brief about how we prove this. This is easy to prove once you have Rolle's theorem, okay? But it's a little bit of a trick. So if you watch the video about the proof, what are they really doing? They're saying, well, this is just like Rolle's theorem, only it's on a slant, right? That's what we were saying. So if we can kind of pull it down like this, then we can use Rolle's theorem. And that's exactly what they do. We define a new function, which is basically the original function more or less minus this secant line, and then it'll go down, it'll be flat. Your f of a is then equal to your, well, not your f, your new function, we'll call it whatever, g or h or whatever you want to call it. So the new function has the equal endpoints. You can then find the point c where it's equal to 0, and then you can back it out, and you'll end up with this. So that's how that proof goes if you want to watch the video on it. So here's an example problem with the mean value theorem. First of all, it says verify that the function satisfies the assumptions of the mean value theorem. So we need our function to be continuous on the closed interval and differentiable on the open interval. Well, of course, that's no problem here because this is just a polynomial. So it's continuous and differentiable everywhere. Fine, good. So now all I have to do is find what c is. Now remember what I said is that f primed of c has to be f of b minus f of a over b minus a, right? So let's figure out what those things are. Now in this case, my a is -2 and b is 2, so this would be f of 2 minus f of -2 over 2 minus -2. Okay, whatever the heck this is. So let's figure out that. Let's see, f of 2 is going to be 8 minus 6 plus 2. So that would be 2 plus 2. Yay! Look at me. And then f of -2 would be -8 plus 6 plus 2. So that's 0. So 4 minus 0 over 4. So 1. Okay. So I want to solve for f prime. I want to solve for c, knowing that f primed of c is 1. Okay, here's f of x. F primed of x is 3x squared minus 3. So f primed of c is 3c squared minus 3. And I want that to be equal to 1. So what I have, 3c squared is 1 plus 3. All right, so c squared is 4/3. c is plus or minus 2 over root 3. Okay, so there are my two c's, right? And they're both going to be in the interval because the interval is from -2 to 2. So that's it. Really straightforward stuff. There, all I have to say about that.